Welcome to the video explanation for Griffiths problem 4.17. 4.17 is split into two parts. Part A asks us to find the eigenvalues and normalized eigenspinors of the spin matrix Y. Part B asks us if we were to measure Sy on an electron in the state alpha beta, what values might we get and what the probability of measuring each one would be. Sy, the spin matrix Y, is highlighted below. We'll begin with 4.17a, in which we will determine the eigenvalues and the normalized eigenspinors of Sy. So first we'll start with the eigenvalues of Sy, and we can determine those using the characteristic equation, which is determinant of Sy minus lambda I is equal to 0. So if we follow through with that computation, we'll get lambda is equal to plus or minus h bar over 2, and these are the eigenvalues of Sy. Now we want to find the corresponding eigenvectors for each of the eigenvalues that we found previously. So starting with lambda 1 is equal to plus h bar over 2, we can plug this into the following equation below, which is Sy minus lambda 1 I, all multiplied by chi. Where I is the identity matrix, lambda 1 is the eigenvalue, and chi is the eigenvector. So we follow through with the computation, and we end up with a system of equations, which we end up getting, if we designate chi 1, 1 to 1, then we'll get chi 1, which is the first eigenvector, as 1i. And similarly, we're going to do the same thing with lambda 2 is equal to minus h bar over 2, so it's really just the same thing. We get a system of equations, we solve that system of equations, and we get designating chi 2, 1 as 1, then we'll get chi 2, which is the second eigenvector, as 1, negative I. So in summary, the eigenvalues are lambda 1 and 2, or lambda 1, 2 is equal to plus or minus h bar over 2, and the corresponding eigenvectors, chi 1, 2, are equal to 1 and plus or minus I. So the normalized eigenspinors are chi 1, 2 is equal to 1 over root 2, and plus or minus I 1 over root 2. And the reason why we essentially multiply 1 over root 2 to our existing eigenvector to normalize it is because of the normalization condition. So alpha, the absolute value of alpha squared and the absolute value of beta squared must equal 1. So the normalization condition allows for this to be true. So now moving on to problem 4.17b. If we measured xy on an electron in the state alpha beta, we want to know what values do you get and the probability of each. The first one's pretty easy to answer. The possible values that we could get are the eigenvalues, so that would be plus or minus h bar over 2, and these are the eigenvalues of Sy. To determine the probability of measuring plus or minus h bar over 2 for an electron in the state alpha beta, we need to square the absolute value of the inner product between the state the electron is in and the eigenstate for measuring plus or minus h bar over 2. So the electron is in the state alpha beta, which we can denote using some fancy ket notation, so that's chi. And we take the inner product of chi with chi 1, 2, and chi 1, 2 is the eigenstate for plus or minus h bar over 2. Then we take the absolute value of that inner product and we square it, and then we have our probability. So if we do that for each eigenstate for h bar over 2 and minus h bar over 2, then we'll get the following. So the one on the calculation on the left is the probability of measuring positive h bar over 2, and The calculation in the lower right is the probability of measuring minus h bar over 2. That's L.